Everyone fears black holes because they can swallow stars. But the most terrifying object in the universe doesn't need to swallow anything. A magnetar is only the size of a city, yet it can unleash enough energy in a fraction of a second to outshine entire regions of the Milky Way and send deadly radiation racing across space with no advance warning. Meet the magnetar, not a cosmic trap, but the universe's ultimate sniper. By the end of this video, you'll never look at the night sky the same way again. Get ready. We begin. Pick up a teaspoon. Go ahead, the one sitting next to your coffee mug right now. The one you've used 1,000 times without a second thought. It weighs maybe 5 grams. A trifle. So light, you could balance it on the tip of your finger and barely feel it. In the grand arithmetic of your morning, it registers as nothing. A spoon, sugar, coffee, the most unremarkable sequence of events in the American kitchen. Now, hold that image in your mind, because we're about to destroy it. That same teaspoon, filled not with sugar, but with matter from a neutron star, would weigh approximately 4 billion tons, not 4 billion pounds, not 4 billion kilograms, 4 billion tons. That is roughly equal to the combined weight of every single car currently registered and driving on every road, highway, and parking lot across the entire United States, crammed into a volume the size of a sugar cube. 1 teaspoon, one number. And your entire intuition about what matter is and how it behaves just collapsed on the kitchen floor. This is not science fiction. This is a measurement. According to NASA, the density of a neutron star sits at approximately 10 to the power of 17 kilograms per cubic meter. That is 100 million billion kilograms packed into a single cubic meter. To put that in perspective, that density is greater than the density of an atomic nucleus itself. We are not talking about something merely heavy, like lead or tungsten or depleted uranium. We are talking about matter compressed beyond the point where normal atoms can exist. The electrons, the empty space, the delicate architecture of chemistry, all of it, gone. What remains is something the universe only makes in its most violent moments. So let's try to build a picture of this, because the number alone doesn't land. Numbers that large tend to slide off the mind like water off glass. Imagine you could take the entire Rocky Mountain range, every peak, every ridge, every billion tons of granite from Montana down to New Mexico, and compress it into a shoebox. That shoebox would be absurdly, catastrophically dense. You couldn't lift it. You couldn't move it. The floor beneath it would collapse. Now take 500,000 of those shoeboxes, each one containing the entire Rocky Mountains, and compress all of them together into a single marble. You are still not at neutron star density. You haven't even gotten close. That is the scale of what we are talking about. And the size of the object holding all this? Roughly 20 kilometers across, about 12 miles in diameter. That is the distance from downtown Chicago to the outer suburbs. You could drive it in 15 minutes on an empty highway. A neutron star containing 1.4 times the mass of our entire sun fits inside that drive. The sun, by comparison, is about 1,400,000 kilometers in diameter. That same mass, squeezed down to 20 kilometers. Every atom of a star that once burned for millions of years, now packed into something smaller than most American counties. But density alone is only the beginning. Because what density creates, on the surface of a neutron star, is gravity that defies every instinct you've ever had about falling. Surface gravity on a neutron star is approximately part 100 billion times stronger than the gravity you feel right now. 200 billion times. If you were somehow standing 1 meter above the surface of a neutron star and you let go, you would hit the surface at approximately 7 million kilometers per hour. In that single impact, your body would release energy equivalent to a nuclear bomb, not from the bomb you're carrying, from the collision itself, from you, falling 1 meter, and that all of that is just a neutron star, the ordinary kind, the baseline model, the entry-level version of this class of object. Magnetars are something else entirely. If you've been quietly worrying about those extra pounds after Thanksgiving dinner, here's a cosmic reality check. A neutron star laughs at every diet ever invented. Gravity there makes weight an entirely new category of problem, one that no amount of cardio will solve. But the insane density we've just walked through, that's only the prerequisite. To build a magnetar, the universe needs one more ingredient, a secret it adds in the very first seconds after the star dies. What happens in those seconds will completely change the way you understand magnetic force forever. So what actually creates a neutron star in the first place? What kind of event does the universe need to run in order to produce something with the density we just spent an entire section trying and largely failing to fully comprehend? The answer is the most violent class of event the laws of physics permit. And it begins with a star. Not just any star, a giant. A star anywhere from 8 to 20 times more massive than our sun. A furnace so enormous that if you placed it at the center of our solar system, it would swallow Mercury, Venus, Earth, and Mars without noticing. These stars burn ferociously. They consume their fuel at a rate so accelerated that while our sun will live for approximately 10 billion years, these giants burn out in as little as a few million. They live fast. They die faster. And the way they die is unlike anything else in the observable universe. When the fuel finally runs out, the core collapses. And here is where language starts to fail. Because the word collapse implies something slow, a building coming down, a structure sagging, a gradual surrender to gravity. This is nothing like that. The core of a massive dying star collapses in less than 1 second, faster than you can blink, faster than a single nerve impulse can travel from your fingertip to your brain. In the time it takes you to register that something has happened, the entire core of a star, a ball of material containing more mass than our sun, previously held up by the outward pressure of nuclear fusion burning for millions of years, has already finished collapsing. During that collapse, temperatures in the core exceed 100 billion degrees Kelvin. 100 billion. The surface of our sun sits at roughly 5,800 degrees Kelvin. The core of a nuclear bomb detonation reaches about 100 million degrees Kelvin. The collapsing stellar core blows past both of those numbers by factors that make comparison almost meaningless. At those temperatures and pressures, something extraordinary happens at the subatomic level. Electrons, the negatively charged particles that orbit atomic nuclei in every piece of matter you have ever touched, are literally forced into protons, crushed into them by gravity so intense that the electromagnetic repulsion that normally keeps them apart simply ceases to matter. When an electron merges with a proton, two things are produced: a neutron and a neutrino. This process happens simultaneously across the entire collapsing core, producing an eruption of neutrinos so catastrophic in scale that the numbers involved are almost theological. The neutrino burst, released in a core collapse supernova, carries energy approximately 300 times greater than the total energy our sun will radiate across its entire 10 billion year lifespan, 300 times the lifetime output of a star like ours. Released in a matter of seconds, neutrinos are particles so weakly interacting that a beam of them could pass through a wall of lead 1 light-year thick and barely be affected. And yet the core collapse produces so many of them, at such density, that even neutrinos struggle to escape immediately. That is how extreme the conditions are. We know this is not theory. We have watched it happen. On February 23, 1987, light from a supernova in the Large Magellanic Cloud, a satellite galaxy of our own Milky Way, located approximately 168,000 light-years away, reached Earth. Astronomers designated it SN 1987A. It became the closest observed supernova since Johannes Kepler watched one in 1604. And it gave scientists the first direct opportunity to test the core collapse model against real observational data. Neutrino detectors buried deep underground in Japan, the United States, and the Soviet Union simultaneously recorded a burst of neutrino interactions lasting approximately 13 seconds. The timing, the energy levels, the number of detections, all of it aligned with the theoretical models developed by researchers, including Hans Bethe and Robert Wilson in 1985, and independently by Vladimir Imshenik and Dmitry Nadyozhin. The core collapse model was not just confirmed, it was confirmed with a precision that left little room for doubt. Those foundational models remain valid today. Now, what does the universe look like in the aftermath? The outer layers of the star, the vast envelope of gas and heavier elements that surrounded the core for millions of years, are blasted outward by the shock wave of the collapse and the neutrino pressure behind it. They expand into space at velocities of tens of thousands of kilometers per second, glowing at temperatures hot enough to outshine an entire galaxy. If our sun were a 60-watt light bulb sitting in your living room, a supernova would be a continuous lightning bolt, bright enough to read by from across the continental United States, and it would sustain that brightness not for a moment, but for weeks, months. The expanding shell of expelled material forms what astronomers call a nebula. The Crab Nebula, visible through even a modest backyard telescope from anywhere in the continental United States on a clear night, is the direct remnant of a supernova observed by Chinese astronomers in the year 1054. That glowing, tangled structure of gas and light is the gravestone, the obituary written in plasma. And at the center of that expanding wreckage, where the core used to be, a ball of neutrons, roughly 20 kilometers across, the object we spent all of Part 1 trying to understand. But now it is doing something that Part 1 did not prepare you for. It is spinning. When the core collapses, it conserves angular momentum, the same physical principle that causes a figure skater to spin faster when she pulls her arms inward. As the core shrinks from something the size of Earth down to something the size of a city, it spins up to rotational speeds that are almost comedic in their extremity. Some newly formed neutron stars rotate at hundreds of revolutions per second. The fastest known pulsar, PSRJ 1748-244-E6 AD, rotates at 716 revolutions per second. 716 complete rotations every single second. Your kitchen blender at its highest setting spins at roughly 100 revolutions per second. The fastest neutron stars spin more than 7 times faster than that, while containing 1.4 times the mass of the sun. Think about your blender spinning at 716 revolutions per second in your kitchen. Now, pack 1.4 solar masses into it. Welcome to the universe's morning routine. That insane rotational speed, and this is the critical point, is not just a curiosity. It is not merely an impressive number to file away. That spin rate is the key to everything that comes next. Because in roughly 10% of cases, that rotation speed combines with something deep inside the collapsing core to generate what physicists call the strongest magnetic field in the known universe. And that magnetic field does not simply exist. It bends the laws of physics themselves. You have a refrigerator magnet, maybe several, a souvenir from a national park, a pizza place coupon holder, a little ceramic tile your grandkid painted at summer camp. It sticks to the fridge door. It holds up a grocery list or a birthday photo. It does its small, dependable job every single day without demanding any attention whatsoever. That magnet generates a magnetic field of roughly 50 Gauss. 50. You can pull it off the refrigerator door with 2 fingers and barely notice the resistance. Now step into a hospital, specifically into the room where they run an MRI scan. You have probably been inside one that loud, tunnel-shaped machine that takes detailed images of the soft tissue inside your body without cutting you open. Before you enter that room, the technician asks you to remove all metal objects, your watch, your belt buckle, your keys, any jewelry. Because the magnetic field inside an MRI machine runs between 10,000 and 30,000 Gauss, roughly 15,000 times stronger than your refrigerator magnet, That field is powerful enough to pull iron-containing objects across the room at dangerous velocity. It is powerful enough to image the interior of the human brain, to distinguish between different types of tissue, to detect tumors millimeters in size. Hospitals treat that room with serious caution. The warnings are posted on the door. The protocols are strict, 10,000 to 30,000 Gauss. That is the strongest magnetic technology most human beings will ever encounter in their lives. The magnetic field of a magnetar is approximately 1 quadrillion Gauss, written as a number 1 followed by 15 zeros, 1,000 trillion Gauss. According to NASA Goddard Space Flight Center's documentation on soft gamma repeaters and magnetars, this figure 10 to the 15th power Gauss represents the strongest magnetic fields confirmed to exist anywhere in the observable universe. Let's translate that into something your instincts can work with. Compared to your refrigerator magnet, a magnetar's field is 1 trillion times stronger. Not 1 million, not 1 billion, 1 trillion. If your refrigerator magnet were a single candle flame, the magnetar's field would be every star currently burning in the Milky Way galaxy, all at once. Compared to the most powerful MRI machine currently operating in any hospital anywhere on Earth, the magnetar's field is 100 billion times stronger. 100 billion times the machine that requires you to empty your pockets before entering the room. 100 billion times the field that can see through your body. These are not incremental differences. These are not steps along the same spectrum. This is a different category of physical reality. So how does the universe build something like this? How does a collapsing stellar core already spinning at hundreds of revolutions per second in those first chaotic moments after the supernova? As we established in the previous section, translate raw rotational energy into a magnetic field of this magnitude. The answer lies in a process physicists call the dynamo effect. You're already living inside a version of it. The Earth generates its own magnetic field through the motion of its liquid iron outer core, molten metal churning and circulating as the planet rotates, generating electric currents, and those currents producing the magnetic field that deflects solar wind and keeps compasses pointing north. It is an elegant, well-understood mechanism, and it has been operating steadily for billions of years, producing a field of roughly half a Gauss at Earth's surface. Now take that same fundamental principle, rotating, conducting fluid, generating a magnetic field through its motion, and apply it to the interior of a newly collapsed neutron star. The core is no longer iron. It is a superfluid of neutrons, compressed to densities beyond atomic nuclei, spinning at potentially several hundred revolutions per second in the first moments of its existence. The convective flows inside that object, the churning, circulating currents of neutron superfluid, driven by the intense temperature gradients left by the collapse, behave as an extraordinarily efficient electromagnetic dynamo. The faster the rotation, the more violent the convection, and the more powerful the magnetic field that results. This theoretical framework was developed and formalized by astrophysicists Christopher Thompson and Robert Duncan in 1992 and 1993. Their model demonstrated that neutron stars born with sufficiently rapid initial rotation, those spinning fast enough in the first second of their existence, could amplify their magnetic fields to the 10 to the 15th Gauss range within the first 10 seconds after formation. The scientific community has broadly accepted this model, and subsequent observations of magnetar behavior have continued to align with its predictions. The critical threshold is that initial spin rate. Not every neutron star becomes a magnetar. In fact, only approximately 10% of them do. The ones that miss the cutoff, those that form rotating slightly too slowly, for reasons tied to the specific conditions of the progenitor star and the dynamics of the collapse, settle into the moderately strong magnetic fields of ordinary pulsars. They are still extraordinary objects by any earthly measure. But they are not this. The 10% that do cross the threshold become something the rest of the universe has to reckon with. Their magnetic fields amplify to levels that do not merely exceed human engineering. They exceed the conditions under which ordinary physics operates without modification. The universe in its vast and indifferent way, essentially runs a sorting process at the moment of stellar death. 90% of neutron stars receive one version of existence. 10% receive something categorically different, something that operates by rules the other 90% never encounter. The universe is basically telling 10% of its neutron stars, you get the harder exam. And that exam involves magnetic fields capable of tearing a planet apart at the molecular level. But here is the thing about the number 10 to the 15th Gauss. It is just a label. It is just a measurement tag we attach to the phenomenon so we can write it in papers and compare it to other things. The number itself, sitting on a page, does not convey what that field actually does when it makes contact with matter, with atoms, with the structure of space itself, because at that strength, even the vacuum, the empty space between objects, the nothing that you think of when you think of outer space, is no longer empty. 3 separate phenomena occur in the immediate environment of a magnetar that have no analog anywhere else in the observable universe. 3 distinct breakdowns of the physical rules that govern everything you have ever seen, touched, or experienced. We are going to walk through each one in turn, carefully, completely, because each one alone is already more disorienting than most people encounter in an entire lifetime of thinking about the natural world. And together, they describe a region of space so physically alien that the universe operating there and the universe you live in share the same laws only in the loosest theoretical sense. The first phenomenon is what happens to atoms themselves. A hydrogen atom, the simplest atom in existence, the most abundant particle of matter in the entire universe. The primary ingredient of every star that has ever burned is, under normal conditions, approximately spherical. Its diameter sits at roughly 1 angstrom, which is 1/10,000,000th of a meter. At its center sits a single proton. Around that proton, a single electron occupies a diffuse, roughly spherical cloud of probability, not a fixed orbit, but a 3-dimensional region of space in which the electron is statistically likely to be found at any given moment. Under no external pressure, with no dominant field interfering, that region is essentially round. This is the atom, as chemistry has always known it, as biology depends on it, as every molecule in your body relies on it to be, in order to form the bonds that hold your DNA together, that build your proteins, that maintain every cell you are made of. Place that atom inside the magnetic field of a magnetar, and the shape is gone. The field lines threading through the space around a magnetar are so catastrophically powerful that they overwhelm every other force acting on the electron. The electron, which normally explores 3-dimensional space freely around the nucleus, is now confined, locked, forced into an extremely tight orbital path, running strictly along the direction of the magnetic field lines, with almost no freedom to move perpendicular to them. The result is that the hydrogen atom, that round 1 angstrom structure, is stretched violently into a cylinder, a needle. The atom elongates to more than 200 times its normal width along the field direction, while being compressed to a fraction of its original diameter across. The geometry of the most basic unit of matter in the universe has been rewritten by force. To visualize this, take a standard basketball, 9.5 inches across, a near-perfect sphere. Now compress that basketball, same matter, same atom, no material removed into a toothpick. That ratio, roughly 200 to 1, is what a magnetar's field imposes on hydrogen, not on exotic particles, not on rare elements, on hydrogen, the most common thing in the cosmos, deformed beyond the recognition of any chemistry textbook ever written. This was calculated rigorously by Dong Lai and Edwin Salpeter in 1991, and further developed by Reuter and colleagues in 1994, detailed quantum mechanical treatments of atomic structure under extreme magnetic field conditions that remain scientifically valid today. Every atom in the environment of a magnetar is a needle. The periodic table, in its entirety, deformed. The second phenomenon involves not matter, but the space between matter. Empty space. The vacuum? Under normal conditions, under every condition, Maxwell's equations were designed to describe a vacuum is optically inert. Light passes through it without bending, without slowing, without any interaction at all. Vacuum has no refractive index. It has no polarizing properties. It does nothing to light because there is nothing there to do anything. This is not a simplification. This is a cornerstone of classical physics, standing undisturbed for more than a century. Quantum electrodynamics. The framework describing how light and matter interact at the deepest quantum level, among the most precisely tested theories in the history of science, predicts that this changes at a specific field strength. That threshold is 4.4 times 10 to the 13th Gauss. At and above this value, which physicists call the QED critical field, the vacuum itself begins to behave as a physical optical medium. Light traveling through it in different directions relative to the magnetic field lines experiences different refractive indices. It bends differently. It polarizes differently depending on orientation. It behaves in measurable and predictable ways, as though it is passing through glass or crystal rather than through nothing. This phenomenon carries the name vacuum birefringence. A Magnetars field exceeds 4.4 times 10 to the 13th Gauss by several thousand times. In 2016, astronomers using the Very Large Telescope of the European Southern Observatory observed light from a neutron star designated RxJ 1855 6.5-3754. They measured a degree of linear polarization in that light that empty space should not be able to produce, but that vacuum birefringence, as predicted by quantum electrodynamics, would produce exactly. The results were published by Mignani and colleagues in the monthly notices of the Royal Astronomical Society in 2016. It was the first observational confirmation of vacuum birefringence outside of a controlled laboratory setting. Empty space, sufficiently magnetized, bends light. Nothing has learned to behave like something. The third phenomenon does not merely deform matter or alter the behavior of light. It manufactures matter from pure field energy with no raw material as input. In 1951, physicist Julian Schwinger demonstrated mathematically, within the framework of quantum electrodynamics, that a magnetic field of sufficient strength could spontaneously generate pairs of particles directly from the quantum vacuum. Specifically, pairs of electrons and positrons, matter and antimatter counterparts, pulled simultaneously into physical existence. The quantum vacuum, unlike the classical vacuum, is not truly empty. It fluctuates continuously with virtual particle pairs that flicker into momentary existence and annihilate each other almost instantaneously, leaving no lasting trace under ordinary circumstances. But a field strong enough at or beyond that same critical threshold of 4.4 times 10 to the 13th, Gauss can physically separate these virtual pairs before annihilation occurs, converting magnetic field energy directly into real, stable, measurable particles, matter generated from energy alone in open space, with nothing as the starting ingredient. The Schwinger threshold is 4.4 times 10 to the 13th Gauss. A magnetar exceeds it. The vacuum surrounding a magnetar may be continuously boiling with electron-positron pairs being torn into physical existence by the field itself, sustained purely by magnetic energy. This is not speculation. The theoretical basis is fully confirmed within quantum electrodynamics. Indirect observational support comes from the X-ray and gamma-ray spectra recorded from known magnetars spectral features consistent with pair production processes operating in extreme magnetic environments. Now hold all three of these together at once. Within a few hundred kilometers of a magnetar atoms are needles, stretched to 200 times their natural length by field lines that permit no other geometry. The vacuum bends light like glass. Because empty space has acquired optical properties it was never classically supposed to possess. and particles materialize continuously from the quantum vacuum, crystallized into existence from pure magnetic energy with no matter required as input. Newton's mechanics, Maxwell's electromagnetism, and the quantum field theory built on Einstein's legacy, all three strained, overridden, or operating in heavily modified form within the same compact region of space. The universe is running a physics modification around a magnetar that humanity did not have the mathematics to even describe until the 20th century. And unlike every software update you have ever received, this one arrived with no instructions, no patch notes, and absolutely no option to roll back to the previous version. Now you understand the outer layer of what a magnetar does to the space around it, but something else has been happening this entire time, something the field has been doing, not to surrounding space, but to the magnetar itself, to its own structure, to its own interior, compressing and twisting layer by layer, year after year, decade after decade. That energy does not radiate away. It does not quietly escape. It accumulates and accumulates and accumulates until there is simply no more room left to contain it. Think about Hoover Dam. If you have ever driven along the Nevada-Arizona border and stood at the edge of that structure, you understand something instinctively that no physics textbook can fully convey. 726 feet of concrete holding back Lake Mead, the largest reservoir by volume in the United States, containing approximately 9.3 trillion gallons of water at full capacity. That dam has been doing its job since 1936. Decade after decade, the water presses, the pressure never relents, never takes a day off, never decreases. And the dam holds because it was built to hold, because its materials are strong enough, because the engineers calculated exactly how much stress the structure could absorb before failure. But every engineer who has ever worked on a dam will tell you the same thing. The question is never whether the pressure exists. The pressure always exists. The question is always the same: how long before something gives? If the image of a dam feels too large, consider something simpler. A spring, a coil of steel sitting on your workbench, being compressed slowly, one turn of the vise per day, every day, for years. Slowly, patiently, each incremental compression barely noticeable on its own, but the energy being stored in that spring does not disappear between compressions. It accumulates. Every day adds to what was already there, and the tighter it gets, the more violent the release will be when the vise finally strips its thread and the spring has nowhere left to go but out. A magnetar is both of these things simultaneously. It is the dam and the spring, and what it is holding back makes Hoover Dam look like a garden hose with a thumb over the end. The outer layer of a neutron star, and therefore of a magnetar, is not rock. It is not metal in any sense you would recognize from everyday life. It is a crystalline lattice of heavy ions, primarily nuclei of iron and nickel, compressed and locked into a rigid geometric structure by the same gravitational pressure that gives the star its extraordinary density. This material, the crust of a neutron star, is approximately 1 billion times harder than steel. Not 1 billion times heavier, 1 billion times harder, meaning 1 billion times more resistant to deformation under stress. No material humanity has ever synthesized, discovered, or theorized in any terrestrial context comes close to this. In 2009, Charles Horowitz and Kai Kadau published molecular dynamics simulations of neutron star crust material in Physical Review Letters, concluding that it is the strongest known material in nature, the hardest substance the universe has produced, and it forms a layer roughly 1 kilometer thick around the exterior of the neutron star, thin relative to the star's total size, like the skin of an apple compared to the fruit beneath, but absolutely, catastrophically rigid. Beneath that crust lies something completely different. The interior of a magnetar, its core is a superfluid of neutrons, a quantum liquid that flows without friction, without resistance, subject to different physical rules than the solid crust above it. This creates a fundamental mechanical tension at the boundary between the two regions. The solid crust wants to behave like a solid rigid, locked in place, resistant to movement. The superfluid interior moves according to its own dynamics, rotating and shifting in ways that do not always synchronize perfectly with the crust above it, and threading through both of them, through the crust, through the core, out into the space surrounding the star, is the magnetic field. 10 to the 15th Gauss. Not static, not fixed, alive, in the sense that it continuously evolves, shifts, and reconfigures as the interior of the star churns beneath it. The magnetic field lines are anchored in the crust on one end and rooted in the superfluid core on the other. As the core moves and the crust resists, those field lines are twisted, slowly, relentlessly, like wringing a wet towel, except the towel is the hardest material in the universe, and the hands doing the wringing are magnetic forces powerful enough to deform empty space. Each individual twist is small. Each incremental stress added to the crystal lattice of the crust is, in isolation, unremarkable. But the field never stops twisting. It does not rest between sessions. It does not allow the crust to recover between compressions the way a metal beam might partially relax between loads. The stress accumulates continuously, building on what came before, adding layer upon layer of mechanical tension into a material that, for all its extraordinary hardness, is not infinitely hard. Nothing is infinitely hard. Every material in the universe has a breaking point, even the strongest. Now consider what is being stored in that field while all of this twisting is happening. The total magnetic energy contained in a typical magnetar runs to approximately 10 to the 46th power erg. Written in terms more familiar, that is roughly 10 to the 25th power tons of TNT equivalent. To give that number a reference point, that means something our sun radiates energy at a rate of approximately 3.8 times 10 to the 33rd power erg per second. In 1 million years of continuous, uninterrupted shining, the sun releases approximately 1.2 times 10 to the 46th power erg of total energy. That is the number, 1.2 times 10 to the 46th power erg across 1 million years of a star burning. A magnetar holds that quantity of energy stored in its magnetic field, not radiated over 1 million years, but contained, locked inside a structure roughly 20 kilometers across, waiting. These figures come from the foundational work of Christopher Thompson and Robert Duncan, published in 1996, confirmed and elaborated in the Comprehensive Review by Woods and Thompson in 2006. 1 million years of sunlight, packed into something smaller than the distance across most American cities, held in place by the hardest material the universe has ever made, being twisted tighter every second by a magnetic field that never sleeps. If a magnetar received an electricity bill calculated at standard California residential rates for the energy stored in its magnetic field, that bill would exceed the gross domestic product of the entire global economy multiplied by 1 million. The utility company would need its own astrophysics department just to process the invoice. But here is the thing that matters. That energy cannot accumulate forever. The hardest material in the universe is still a material. It still has a threshold. It still has a point beyond which no amount of hardness is sufficient to hold what is being pressed against it from inside. And when that threshold is finally crossed, not gradually, not with warning, not with a slow creak that gives you time to step back, something happens in a fraction of a second that releases energy on a scale that makes everything we have described so far look like a warm-up act. And that release is so extreme, so total and so fast that even light itself cannot carry a warning ahead of it. There is a basic rule of thermodynamics that everything in your daily life obeys without exception. When something gets hot, it releases that heat outward. A cast iron skillet pulled from the oven radiates heat into the kitchen. A car engine running at operating temperature continuously sheds thermal energy through its cooling system, through the exhaust, through the metal of the block itself. A campfire pushes warmth outward in every direction simultaneously. This is not a design choice. This is physics. Heat moves from regions of higher concentration to regions of lower concentration, always, without negotiation, until equilibrium is reached. Every hot object you have ever encountered in your life has followed this rule without a single exception. A magnetar does not follow this rule, not because the rule is wrong, but because the magnetic field surrounding a magnetar is strong enough to overpower the mechanism by which the rule normally operates. When energy is released near the surface of a magnetar through the stress fractures building in the crust, through the continuous twisting of field lines we examined in the previous section, it does not simply radiate outward into space the way heat leaves a skillet. The released energy superheats the material at and near the fracture point into plasma. Plasma is the fourth state of matter beyond solid, liquid, and gas, a superheated soup of ions and free electrons moving at enormous velocities, carrying extraordinary amounts of thermal and kinetic energy. Under normal astrophysical conditions, plasma expands and radiates energy outward relatively freely. But the magnetic field of a magnetar 10 to the 15th Gauss, threading through every cubic centimeter of space near its surface, acts as a containment barrier. Charged particles, which is what plasma consists of, cannot move freely across magnetic field lines. They spiral along them. They follow them. But crossing perpendicular to a field this powerful is effectively impossible. The magnetic field functions as a wall, an invisible, omnidirectional pressure vessel, built not from any material, but from pure electromagnetic force. The plasma generated near the surface of the magnetar is trapped inside this magnetic enclosure, unable to disperse freely, unable to shed its energy into surrounding space the way physics would normally demand. Picture a bubble of superheated steam sealed inside a thick-walled glass vessel with no outlet valve. The heat has nowhere to go. The pressure builds. The temperature climbs. The steam pushes harder against the glass, which pushes back, which forces the pressure higher still. No release, no equilibrium, just accumulation in a closed system until the glass runs out of tensile strength. The plasma trapped near a magnetar's surface operates on exactly this principle, except the temperatures involved reach into the billions of degrees Kelvin, and the walls of the vessel are made of the strongest magnetic field the universe produces. And now the feedback loop begins. This is where the situation transitions from extreme to catastrophic in its internal logic. A small fracture opens in the crystalline crust, the kind of incremental stress failure that has been building for decades or centuries under the continuous torque of the magnetic field. That fracture releases a quantity of plasma. The plasma is immediately caught by the magnetic field and held in place rather than dissipating. The trapped plasma exerts pressure, thermal pressure, radiation pressure, the pressure of billions of degree material with nowhere to expand. That pressure pushes back against the surrounding crust. The crust, already stressed to near its limit from the ongoing magnetic twisting, develops new fractures under this additional load. Those new fractures release more plasma. The magnetic field traps that plasma too. More pressure, more fractures, each crack feeding the next, each release of plasma adding to the pressure that drives the next release. This is a positive feedback loop in the strictest physical sense, a process that self-amplifies, each small event making the next event more likely and larger. The engineering analogy that fits most precisely is a nuclear reactor experiencing a loss of control chain reaction. Each fission event releasing neutrons that trigger additional fissions. The reaction rate climbing exponentially until the system either reaches a new equilibrium or tears itself apart. In a magnetar, the feedback runs between crust fractures and trapped plasma, each cycle reinforcing the other. The magnetic field acting not as a safety system, but as the mechanism that prevents any early release from relieving the pressure before it becomes total. And here is what makes this particularly unsettling from an observational standpoint. Between episodes, a magnetar can appear almost quiet, soft gamma repeaters. The class of magnetars observed to be actively cycling through burst activity regularly pass through extended periods of low activity. Months of near silence. Years, in some cases, decades during which their output drops to levels that, while still exotic by any earthly standard, give no obvious indication of the internal process continuing to run. The stress in the crust is still accumulating during these quiet periods. The magnetic field is still twisting. The feedback conditions are still developing. The silence is not evidence of safety. It is evidence of patience. The system is loading, and the absence of visible output is simply the interval between the last partial release and the next one, which will be larger for having been delayed. This pattern has been documented across multiple observed soft gamma repeaters, where extended quiescent periods are followed by sudden resumptions of burst activity with no reliable precursor signal detectable in advance. Now consider what the loaded system actually contains at the moment of full release. The combined nuclear arsenal of the United States and Russia, every warhead, every strategic missile, every tactical weapon in the inventories of both nations represents approximately 10 to the 23rd power erg of total explosive yield. That is roughly 10 billion tons of TNT equivalent. The most destructive collection of weapons assembled in human history, sufficient to end civilization and render large portions of the Earth's surface uninhabitable for generations. A single giant flare from a magnetar releases between 10 to the 44th and 10 to the 46th power erg. That means a single magnetar giant flare releases more energy than the combined nuclear arsenals of the United States and Russia by a factor ranging from 100 billion trillion to 10,000 billion trillion times. Not a rounding error, not a matter of degree. A difference so vast that the comparison barely qualifies as meaningful except as a way of anchoring your understanding of what release means in this context. A magnetar does not explode the way we think of explosions. It does not detonate the way weapons detonate. What it does has no name in the human vocabulary of destruction, because nothing in human experience provided the occasion to invent one. The universe would like to remind you, on this otherwise ordinary Monday morning, that the things keeping you up at night here on Earth, the bills, the headlines, the slow grind of daily anxiety are measured against the actual scale of energetic events in the cosmos, essentially indistinguishable from nothing, not metaphorically, mathematically. So what actually happens when the crust finally reaches its absolute limit? When the feedback loop completes and the magnetic trap can no longer hold what it has been compressing? The answer to that question was first observed by scientists in the year 2004, and it did not merely register on their instruments. It reached across 50,000 light-years of open space and physically touched the Earth. Not because we were looking for it, because it was impossible to miss. On April 18th, 1906, at 12 minutes past 5 in the morning, the city of San Francisco was torn apart. The North American plate and the Pacific plate locked against each other along the San Andreas Fault under accumulated stress for decades, finally slipped. The rupture ran approximately 290 miles along the fault line. The ground shifted by as much as 20 feet in some locations. Buildings collapsed. Fires broke out across the city and burned for 3 days. More than 3,000 people died. The energy released by that event measured approximately 10 to the 24th power erg, a number that, at the time, represented one of the most destructive releases of natural energy ever witnessed by human civilization on American soil. 54 years later, on May 22, 1960, the most powerful earthquake ever recorded by modern instrumentation struck off the coast of southern Chile. Magnitude 9.5. The ground shook for approximately 10 minutes. The resulting tsunami crossed the entire Pacific Ocean and killed people in Hawaii, Japan, and the Philippines. The energy released approximately 10 to the 25th power erg, 10 times the energy of the 1906 San Francisco earthquake, enough to reshape coastlines, enough to register on seismographs on every continent simultaneously. These are the largest, most violent geological events our planet is capable of producing. They represent the absolute upper limit of what the Earth's crust, a rocky, dynamic, geologically active shell thousands of miles thick, can do when it finally releases stored stress. They are, by any human measure, catastrophic. A starquake on a magnetar releases approximately 10 to the 42nd power erg. From a small event, from what the universe would consider a minor adjustment, that is 10 billion times more energy than the most powerful earthquake ever recorded on Earth. Not 10 billion times more than San Francisco, 1906. 10 billion times more than Chile, 1960. The absolute maximum our planet has ever demonstrated. And it happens not over 10 minutes of ground shaking, not over a rupture spanning hundreds of miles, but in a fraction of a single second. The crust of a magnetar does not groan and slip gradually. It does not give warning tremors for days beforehand. It fractures in a time frame so short that describing it as instantaneous is barely an exaggeration. If the 1906 San Francisco earthquake, the event that leveled a major American city and burned for 3 days, were the sound of a single quiet handclap, then a starquake on a magnetar would be a thermonuclear bomb detonating continuously for 0.2 seconds. That is the ratio. That is the gap between the most violent thing Earth's geology can produce and what a magnetar considers a routine stress release. Now consider the physical mechanism that produces this. The crystalline crust of a magnetar, that billion times harder than steel lattice of iron and nickel nuclei we examined in Part 5, does not fracture randomly or uniformly. It fractures along structural fault lines, analogous in concept to the geological fault lines that produce earthquakes on Earth, but operating at the atomic and nuclear scale rather than the geological scale. The crystal lattice of the crust develops planes of weakness over time, as the magnetic field continuously applies differential stress across different regions, twisting some sections more than others, loading certain crystal planes more heavily than their neighbors. When the accumulated stress at one of these planes finally exceeds the material's yield strength, the fracture propagates along that plane at enormous speed. The displacement involved is almost incomprehensibly small by earthly standards. We are not talking about tectonic plates shifting 20 feet as they did in 1906 on a magnetar crust. A displacement of a few millimeters or even a single centimeter is sufficient to trigger an energy release of staggering magnitude. The reason is the density of the material involved. When 1 cubic centimeter of neutron star crust, containing the equivalent mass of hundreds of millions of tons, shifts by even 1 centimeter relative to the layer beside it, the kinetic and elastic energy released in that displacement is equivalent to hundreds of millions of tons of TNT. The math is brutal and straightforward. Mass times the square of velocity, integrated across the displacement, produces numbers that the word explosion was not designed to describe. 1 centimeter, hundreds of millions of tons of TNT on a magnetar. That is a small movement. On December 27, 2004, at 21 hours 30 minutes, Coordinated Universal Time, every gamma-ray and X-ray detector operating in the solar system encountered something they were not designed to survive. Instruments aboard 15 separate spacecraft, including the International Gamma-Ray Astrophysics Laboratory, operated jointly by NASA and ESA. The Reuven-Rometty High-Energy Solar Spectroscopic Imager and the CONUS Wind Detector simultaneously registered a signal so powerful that most of them saturated immediately. Saturated meaning the detectors hit their maximum measurable value and stayed there, unable to distinguish the actual peak intensity because the signal exceeded their design limits. It was like trying to measure a fire hose with a kitchen measuring cup. The source was SGR 1806-20, a magnetar located approximately 50,000 light-years from Earth, sitting near the inner regions of the Milky Way. In the first 0.2 seconds of its giant flare, SGR-1806-20 released approximately 2 times 10 to the 46th power erg of energy, 2 times 10 to the 46th power erg in 0.2 seconds. That single initial burst carried more energy than our sun will radiate in 250,000 years of continuous burning. Not 250 years, not 2,050 years, 250,000 years, released in a fifth of a second from an object the size of a city at a distance of 50,000 light years. NASA confirmed the event. ESA confirmed the event. Multiple independent international observatories confirmed the event. The data from Integral, RESI, and CONUS Wind were cross-referenced and published in peer-reviewed literature. This is not a theoretical scenario. This is a documented, measured, multiply-confirmed observation. Think about where you were in December of 2004. The first iPod had been on the market for 3 years. Facebook did not yet exist for the general public. It would not launch beyond Harvard until 2004, and beyond universities until 2006. The Indian Ocean tsunami had just struck on December 26th, the day before, commanding every news network on the planet, and 50,000 light years away, in a direction most people on Earth could not have pointed to on a star map. Something cleared its throat, and the shockwave reached us anyway. But that question, what the event actually did when it reached us, and what it would have done from a shorter distance, that is where the real accounting begins. Because the number in the physics paper is one thing. What it means for a planet with living things on it is something else entirely. At 21 hours, 30 minutes Coordinated Universal Time on December 27th, 2004, 15 spacecraft scattered across the solar system were simultaneously struck by the most intense burst of gamma radiation ever recorded from beyond our solar system. The detectors aboard most of them maxed out within milliseconds. The signal was not merely strong. It was categorically beyond the range these instruments were built to handle, instruments designed specifically to detect high-energy astrophysical events, calibrated for the most extreme phenomena their designers could anticipate. The source, as established in the previous section, was Magnetar SGR-1806-20. In the first 0.2 seconds alone, it released approximately 2 times 10 to the 46th power erg. But the question that matters, the question that changes this from an interesting astronomical measurement into something personally relevant to every living thing on this planet, is what that energy actually did when it arrived here. The answer is documented, measured, published in peer-reviewed scientific literature. The burst of radiation from SGR-1806-20 was powerful enough, even after traveling 50,000 light-years through interstellar space, to compress the Earth's magnetosphere. The magnetosphere is the magnetic bubble generated by Earth's own core that extends tens of thousands of kilometers into space, deflecting the continuous stream of charged particles flowing outward from the sun. It is, in practical terms, the planet's primary shield against high-energy radiation from space. The spacecraft Champuga, operated by the European Space Agency, detected measurable compression of this structure, the magnetosphere physically pushed inward by the pressure of radiation arriving from 50,000 light-years away. Simultaneously, the burst ionized Earth's ionosphere, the upper layer of the atmosphere, sitting between approximately 60 and 1,000 kilometers above the surface, where solar radiation normally strips electrons from atmospheric atoms during daylight hours. The night side of Earth, which should have been electrically quiet and dark, was suddenly behaving as though it were exposed to full daylight ionization. The distinction between the lit and unlit hemispheres of Earth, in terms of ionospheric electrical behavior, was temporarily erased by radiation from an object 50,000 light-years distant. This was not inferred from indirect evidence. It was measured directly and documented by Omran Inan and colleagues, published in Geophysical Research Letters in 2007. Precise measurements of ionospheric disturbance correlated with the arrival time of the SGR 1806-20 flare, recorded by very low-frequency radio receivers that monitor ionospheric conditions continuously, 50,000 light-years, 470 million trillion kilometers of open space between the source and the detector, and the signal was still powerful enough to alter the electrical behavior of Earth's upper atmosphere and measurably compress the planet's magnetic shield. Take a moment with that distance, 470 million trillion kilometers. If you drove a car at 60 miles per hour without stopping, no sleep, no fuel breaks, continuous motion from the moment the universe was born, you would not have covered that distance yet, light itself. Traveling at approximately 300,000 kilometers per second took 50,000 years to make the crossing, and after all of that, after 50,000 years of traveling through the near vacuum of interstellar space, losing intensity with every light year according to the inverse square law, what arrived was still strong enough to physically move Earth's magnetic field and light up the night side of the planet. Now, apply the inverse square law in the other direction. Radiation intensity falls off with the square of distance. Double the distance, quarter the intensity. Halve the distance, quadruple the intensity. SGR 1806-20 sits approximately 50,000 light-years from Earth. The nearest star system to our own Alpha Centauri sits approximately 4.2 light-years away. If SGR 1806-20 had been located at 10 light-years distance instead of 50,000 light-years, roughly twice the distance to Alpha Centauri, well, within what astronomers consider our immediate stellar neighborhood, the geometry of the inverse square law produces a specific number. 5,000 times closer means 25 million times more intense radiation arriving at Earth. 25 million times the intensity of an event that already compressed our magnetosphere and ionized our night-side atmosphere from 50,000 light-years away. The result, modeled and discussed in the scientific literature, including the analysis published by Palmer and colleagues in Nature in 2005. The primary peer-reviewed paper documenting the SGR 1806-20 event and its terrestrial effects would be the complete destruction of Earth's ozone layer, not partial depletion, not the kind of damage measured in percentage points that we associate with industrial chemical emissions. Total destruction. The ozone layer, stripped away entirely, would leave the surface of the Earth exposed to levels of ultraviolet radiation lethal to most surface life. The bombardment would not last hours or days. It would persist for years, for as long as the upper atmosphere remained unable to regenerate its protective chemistry faster than incoming radiation could break it down again. And here's the fact that separates a magnetar from every other dangerous object in the universe, including black holes. You do not need to travel toward it. You do not need to fall into it. You do not need to cross any threshold or approach any boundary. The danger does not wait for you to make a mistake in navigation. It travels to you at 300,000 kilometers per second across any distance the universe contains, silently, with no forerunner, no detectable warning signal that arrives before the radiation itself. Because nothing travels faster than the radiation, a black hole sits and waits. It is the universe's passive trap, dangerous only to whatever chooses, or falls, to cross its event horizon. Stay away from a black hole, and a black hole cannot harm you. The geometry is that simple. A magnetar does not wait. It does not require your cooperation or your proximity. When it releases a giant flare, it sends lethal energy outward in every direction simultaneously. At the maximum speed the laws of physics permit, across distances that make the word far meaningless as a description of safety. If the universe had traffic laws, a magnetar would be cited for exceeding the speed limit in every spatial dimension simultaneously, and the ticket would arrive at your door before you knew the car had left the driveway. This is the moment where a magnetar separates itself completely from every other category of dangerous object the universe contains, including black holes. Because a black hole simply stands there and waits. Patient, stationary, entirely dependent on your approach. A magnetar does something fundamentally different. It hunts. Think about a bear trap sitting in the woods. Heavy steel jaws, spring-loaded, sitting motionless on the forest floor beneath a thin layer of leaves. It is genuinely dangerous. It can cause serious harm. But there is one absolute condition built into its design that cannot be bypassed. You have to step on it. The trap does not move toward you. It does not sense your presence from a distance and launch itself in your direction. It sits. It waits. It is entirely, completely, 100% dependent on your cooperation, on your foot making contact with its trigger plate. Walk around it, step over it, avoid that section of forest entirely, and the trap is as harmless as a rock. Distance is a complete solution. Awareness is a complete solution. The danger is real, but it is fundamentally passive. Or consider something even simpler. A pothole in the middle of a highway, deep enough to damage an axle, wide enough to catch a tire off guard at speed. Dangerous, costly, potentially catastrophic if encountered at the wrong moment. But only if you drive into it, only if you fail to see it, fail to swerve, fail to slow down in time. Keep your eyes on the road, and the pothole cannot reach you. It has no mechanism for reaching you. It simply exists in a fixed location, indifferent to your presence, harmful only through contact that requires your own motion to initiate. Black holes work on exactly this principle. They are the universe's most elegant passive traps. To be consumed by a black hole, you must cross its event horizon, the boundary beyond which the escape velocity exceeds the speed of light. The point of no return from which nothing, not matter, not radiation, not information of any kind, can escape back outward. That boundary is real. It is absolute. What happens beyond it is physics operating at its most extreme. But the event horizon does not expand toward you. It does not send out tendrils of gravity to pull you in from a safe distance in any way that differs from ordinary gravitational attraction. A black hole's gravity follows the same inverse square law as every other gravitating object. At sufficient distance, a black hole of stellar mass is gravitationally indistinguishable from the ordinary star that preceded it. The planets that orbited that star before it collapsed would continue orbiting at the same distances after the collapse, undisturbed, because the gravitational field at those distances has not changed. Sagittarius A star, the supermassive black hole sitting at the center of our Milky Way galaxy, containing approximately 4 million solar masses, located roughly 26,000 light-years from Earth, poses zero direct threat to this planet. Not negligible threat, zero direct threat. NASA's Chandra X-ray Observatory has monitored Sagittarius A star extensively. It occasionally produces flares as material falls into it. It generates X-ray emissions detectable across the galaxy, and at 26,000 light-years distance, none of it matters to us. The radiation is too dilute by the time it crosses that distance to cause meaningful harm. The gravitational influence at that range is real, but utterly dominated by far closer objects. Sagittarius A star is 4 million times the mass of the Sun, and it cannot harm us from 26,000 light-years away. Because we are not approaching it, and it is not approaching us. Stay away from a black hole. That is the entire safety protocol. That is the complete user manual. It has one rule, and the rule is simple. A magnetar has no such rule. A magnetar does not require your approach. It does not need you to make a navigational error or cross any threshold or move in any particular direction. When a magnetar releases a giant flare, it fires energy outward isotropically, meaning equally in all directions, simultaneously at the speed of light, 300,000 kilometers per second, in every direction, toward everything within range, without selection, without targeting, without the requirement that its victims do anything at all except exist within a certain radius when the event occurs. There is no warning. There is no sound space does not transmit sound. There's no visible precursor flash that arrives meaningfully ahead of the lethal gamma radiation, because both travel at the same speed. There is no time to react, because reaction requires information, and the information and the danger arrive simultaneously. A giant flare from a magnetar is the universe's closest approximation to a perfectly silent, perfectly fast, perfectly omnidirectional weapon discharge. The estimated danger radius for significant ozone layer damage from a magnetar giant flare sits at approximately 3,000 to 10,000 light-years, a figure supported by research from Bohdan Podzinski in 1992 and refined through subsequent work by Kevin Hurley and colleagues in 1999 and 2005 studying the behavior and reach of soft gamma repeater events. 3,000 light-years is not a narrow margin. 3,000 light-years is a sphere containing millions of star systems, potentially billions of planets. Any living world sitting within that sphere when a nearby magnetar fires is in serious trouble, and that world does not need to be falling into anything to qualify. As of the current catalogs compiled through 2024 and 2025, the McGill Magnetar catalog lists approximately 29 to 30 confirmed magnetars within the Milky Way. Our galaxy spans roughly 100,000 light-years in diameter. The confirmed magnetars are distributed across various distances, some deep in the inner galaxy, some in the outer regions. The closest confirmed magnetar to Earth among the well-studied objects is 1 E2, 2, 5, 9, plus 5, 8, and 6, sitting at approximately 10,000 light-years distance, SGR 1806-20, whose 2004 giant flare we examined in detail, sits at approximately 50,000 light-years. Neither of these objects is currently in an active flaring state that poses a documented threat to Earth, but 29 to 30 confirmed magnetars in one galaxy is almost certainly a significant undercount. Magnetars that are not currently in active phases. Magnetars whose flares are directed away from our instruments. Magnetars that formed and have already faded below our detection threshold. None of these appear in the catalog. The true population is likely far larger. We see what we can see. The rest remains in the dark. A black hole is a trap at your house dangerous only if someone breaks in. A magnetar is a sniper positioned outside one of your windows, and you have no idea which window or how many snipers there are, or when any of them last fired. But shooting from a distance is not the only method in the magnetar's arsenal. It is simply the one with the longest reach. If you were somehow positioned close enough for the magnetic field itself, not the radiation, but the field to make direct contact with your physical structure, the radiation would be the least of your concerns. What the field does at close range to matter, to chemistry, to the molecular bonds that hold every living thing together, is something no weapon ever designed by human hands has come close to replicating. Not through heat, not through force, not through any mechanism we have ever deployed or imagined deploying. It dissolves you. At the molecular level. Without fire. Without gravity. Without asking. The threat a magnetar poses is not a single fixed thing. It is not one mechanism operating at one scale. It is a graduated series of increasingly total forms of destruction, each one activating at a different distance, each one more intimate and more complete than the last. Think of it as a set of concentric circles drawn around the magnetar, and understand that as you move inward through those circles, what happens to you does not merely get worse in degree. It gets worse in kind. Different physics, different mechanisms, different categories of harm that have no relationship to each other, except that they all originate from the same 20-kilometer object spinning alone in the dark. The outermost circle, the first and most distant layer of danger, sits at a range of approximately 3,000 to 10,000 light-years. This is the gamma radiation zone, the zone where a giant flare does not kill directly, but accomplishes something almost more insidious. It removes the conditions that make survival possible, quietly and completely, before life on the surface has any indication that something has changed. Gamma radiation arriving at this range penetrates the upper atmosphere and interacts with molecular oxygen and nitrogen at high altitude. The photons carry enough energy to break apart ozone molecules, the three-atom oxygen structures, O3, that form the stratospheric layer sitting between approximately 15 and 35 kilometers above Earth's surface. This layer is not merely incidentally useful. It is the specific filter that blocks the wavelengths of ultraviolet radiation, particularly UVB and UVC, that damage biological molecules. DNA absorbs UVB efficiently. Exposure at sufficient intensity breaks DNA strands, disrupts cellular replication, and causes the kinds of cellular damage that accumulate into radiation-induced biological failure across entire ecosystems. Strip the ozone layer and UVB and UVC flood the surface. Flood photosynthetic organisms, the base of virtually every food chain on Earth. The organisms that convert solar energy into the chemical energy that flows upward through every ecosystem are acutely sensitive to UVB exposure. Their photosynthetic machinery is disrupted. Their DNA takes damage faster than cellular repair mechanisms can address it. Population collapse follows, cascading upward through every level of the food web that depends on them. Brian Thomas and colleagues modeled this process in 2005, examining the atmospheric and biological consequences of gamma-ray burst irradiation at various distances and intensities. The results were not ambiguous. Sufficient gamma irradiation at this range category produces a mass extinction event through ecosystem collapse, driven entirely by the removal of ultraviolet shielding, with no direct lethal radiation reaching the surface at all. The magnetar does not need to kill you directly. It simply removes the roof, and the sun finishes the job over the following years. Move inward to the second circle, a few hundred light years. At this range, the radiation intensity crossing the inverse square law threshold climbs to levels where direct biological lethality becomes immediate. The dose of gamma radiation arriving at a planetary surface at this distance from a giant flare is sufficient to deliver lethal radiation exposure to unshielded organisms within seconds of the flare's arrival. The median lethal dose of radiation for a human being, the dose at which 50% of exposed individuals die within 30 days without medical treatment, is approximately 6 gray. A giant flare at a few hundred light years delivers orders of magnitude beyond this threshold in the initial pulse alone, not a survivable exposure requiring treatment. A dose that ends biological function at the cellular level across every exposed organism simultaneously, and there is no shield. This is not a deficiency of current technology that future engineering might address. The gamma rays produced by a magnetar giant flare carry energies that penetrate meters of concrete, centimeters of lead. Any practical thickness of any material humanity has access to or could realistically construct. A nuclear bunker built to survive the blast effects and initial radiation of a surface nuclear detonation would not provide meaningful protection against a giant flare at this range. The radiation passes through the walls. It passes through the rock above the bunker. It passes through you. The third circle is the closest. A few light years the scale of immediate stellar neighbors. At this range, the magnetic field of the magnetar itself, which we have already established as operating at 10 to the 15th Gauss and capable of deforming atoms and creating particles from vacuum, begins to extend its direct physical influence. The magnetosphere of any planet within this range would interact with the outer reaches of the magnetar's field structure, navigation systems, communication infrastructure. Any technology dependent on stable electromagnetic environments, all disrupted or destroyed. But more fundamentally, the physical chemistry of matter itself begins to operate in the modified regime we examined in Part 4. The needled atoms, the optical vacuum, the pair production these effects, while centered on the amagnetar, extend outward in diminishing intensity and at a few light years. Their influence on a planetary environment would be measurable and destructive. Now collapse all three of these circles into a single scenario. A magnetar forms from a supernova of a massive star, the process we examined within 1,000 light-years of Earth. 1,000 light-years places it firmly within the zone where a giant flare produces direct lethal gamma radiation at the surface. There is no advance warning. The light from the supernova that creates the magnetar travels at the speed of light, and the gamma radiation from the first giant flare also travels at the speed of light. You see the birth announcement and the first attack in the same moment, or separated by an interval too short for any response to be organized. There is no defense to mount. There is no evacuation to plan. There is no technology currently existing or foreseeable within the near-term trajectory of human engineering that intercepts or deflects a gamma-ray pulse traveling at the speed of light across 1,000 light-years of space. Astronomers and astrophysicists monitor the sky continuously. Fermi Gamma Ray Space Telescope. SWIFT. Integral. These observatories maintain around-the-clock surveillance of high-energy events across the observable universe. They detect magnetar bursts, they catalog them, they measure their properties, and they confirm, as of the current state of observation, that no known magnetar in an active flaring state is positioned within a dangerous range of Earth on a threatening trajectory. That is a genuine, honest, current assessment. The sky is being watched. Nothing known is coming, but 29 confirmed magnetars in a galaxy of 200 to 400 billion stars means the confirmed catalog represents a vanishingly small fraction of what actually exists. The ones we cannot see quiescent, cooling, oriented away from our instruments, remain uncharted. Which brings us to one of the more quietly disturbing implications of magnetar existence. The Fermi paradox asks a question that has occupied scientists and philosophers for decades given the age of the universe, the number of stars, and the seemingly reasonable probability of life developing elsewhere. Why do we see no evidence of other technological civilizations? Why is the universe so apparently empty of signals, structures, and signatures of intelligence beyond our own? Many explanations have been proposed. Some invoke the rarity of life's origin. Some invoke the difficulty of interstellar travel. Some invoke the possibility of self-destruction. Tisvipiran and Raúl Jiménez, writing in Physical Review Letters in 2014, proposed a different answer. Gamma-ray bursts events closely related to, and in some cases produced by magnetar activity, may have sterilized large volumes of the Milky Way throughout its history. The inner regions of the galaxy, where stellar density is highest and magnetars form most frequently, may have experienced gamma-ray burst irradiation at rates high enough to repeatedly reset any developing biosphere before it could reach complexity. Life gets started, accumulates complexity over hundreds of millions of years, and then a nearby magnetar fires, and the process begins again from scratch. Not once, repeatedly, across billions of years. The outer regions of the galaxy, where we happen to reside, are statistically safer, but not immune. Maybe the answer to the question of why we appear to be alone in the universe is not that nobody else ever existed. Maybe the answer is that there were many others, and the universe had opinions about their continued existence. And now imagine you have somehow survived the gamma pulse, the ozone destruction, the direct radiation. Imagine you are, through some extraordinary circumstance, in close proximity to a magnetar rather than at a safe galactic distance. The radiation is no longer the primary concern. What waits at close range is something no weapon in human history has ever achieved: a mechanism that requires no heat, no explosive force, no gravity, no combustion. It simply reaches into the molecular architecture of whatever you are made of and unmakes it, bond by bond. At the most fundamental level, matter can be addressed, not burning, not crushing, dissolving. At the scale of chemistry itself, there are two fundamentally different categories of danger in everyday life. The first is the kind you can see coming. A truck that has lost its brakes on a mountain road, you hear it. You see it, you have some fraction of a second to react. Maybe you jump, maybe you swerve, maybe the reaction saves you, and maybe it does not. But the opportunity exists. The danger announced itself. It gave you a chance, however slim, to participate in the outcome. The second kind gives you nothing. Carbon monoxide, colorless, odorless, tasteless, producing no sound, no sensation, no perceptible change in the air around you. It fills a room and you feel only a faint headache, then drowsiness, then nothing. No announcement, no window of reaction, no moment where your instincts can fire and your body can respond. The danger completes itself before your nervous system registers that anything has changed. The second kind is always more dangerous, not because it is necessarily more powerful, but because the absence of warning eliminates the only variable that might have made a difference. Time. Keep this distinction in your mind as we examine, side by side, exactly how a black hole kills and exactly how a magnetar kills. Because the comparison is not merely academic, it defines everything that separates these two objects in terms of what they actually mean for anything living within their reach. A black hole kills through what astrophysicists formally call tidal disruption, the colloquial term, coined somewhere in the overlap between physics and dark humor, is spaghettification. The mechanism is this: gravity follows an inverse square law, meaning it weakens rapidly with distance. As you fall toward a black hole of stellar mass, the gravitational pull on the side of your body closer to the singularity is measurably, dramatically stronger than the pull on the far side. That differential, that tidal gradient, stretches your body along the radial direction while simultaneously compressing it laterally. You're pulled longer and squeezed narrower, simultaneously, continuously, with increasing violence the closer you get. The process completes in a fraction of a second for stellar mass black holes. For supermassive black holes, the tidal gradient at the event horizon is gentler, and the process plays out over longer timescales. But here is the critical structural fact. You must travel to the black hole for this to happen. You must cross the event horizon, that boundary beyond which escape is geometrically impossible. The black hole does not extend tidal forces outward to reach you at a safe distance in any way that differs meaningfully from ordinary gravity. At distance, a black hole pulls on you exactly as a star of equivalent mass would. You feel it. You can calculate it. You can counteract it with orbital velocity or with thrust. The danger is real only when you are in the process of falling in. And falling in requires that you either choose to approach or make a catastrophic navigational error. Stay away. That is the complete safety instruction. One rule: absolute effectiveness. A magnetar offers two entirely separate methods of killing, and neither of them requires your approach. The first method operates at galactic range. Gamma radiation, the highest energy form of electromagnetic radiation, the shortest wavelength, the most penetrating, is released in catastrophic quantities during a giant flare. It travels through space at 300,000 kilometers per second. It is completely invisible to the human eye. It produces no sound. It generates no detectable precursor that travels faster than itself and could serve as a warning. When it arrives as the warning and the event simultaneously. There is no gap between notification and impact. When gamma radiation at giant flare intensities reaches biological tissue, it ionizes molecules along its path. In DNA, the double helix structure encoding every instruction your cells use to function, replicate, and maintain themselves. Gamma photons break the bonds holding the two strands together. Double-strand breaks in DNA are the most severe category of DNA damage a cell can sustain. Single-strand breaks can often be repaired. Double-strand breaks overwhelm the cell's repair machinery, particularly when they occur simultaneously across millions of cells throughout the body. The cells cannot replicate correctly. They die, or they replicate incorrectly and trigger cascading failures. The process is not immediate in the way that a physical impact is immediate, but at sufficient radiation doses, it is total and irreversible. The median lethal dose of radiation for a human being, the dose at which 50% of exposed individuals die within 30 days without medical treatment, is approximately 6 Gray. A giant flare from a magnetar at a distance of a few hundred light years delivers a radiation dose of millions of Gray within seconds of arrival, not a slowly accumulating exposure requiring days or weeks to become lethal. An instantaneous delivery of a dose millions of times beyond the threshold of survivability. Completing before any biological response can begin, the second method operates at close range, and it is categorically more strange. At a distance of a few thousand kilometers from a magnetar well within the zone where the magnetic field registers at or near its full strength of 10 to the 15th Gauss, the field acts directly on matter at the molecular level. Chemical bonds are electromagnetic in nature. The bond between two carbon atoms, between carbon and hydrogen, between any of the atomic pairings that constitute the organic molecules making up a living body, involves energies in the range of 1 to 5 electron volts. This is the energy scale at which molecules maintain their structure, at which proteins fold into functional shapes, at which DNA retains its configuration, at which every biochemical process that constitutes life operates. The magnetic field of a magnetar at close range carries energy densities that overwhelm these bond energies completely. As documented in the Foundational Review by Alice Harding and Dong Lai, published in Reports on Progress in Physics in 2006, titled Physics of Strongly Magnetized Neutron Stars, the field restructures the quantum mechanical states of electrons in atoms, forcing them into the elongated cylindrical configurations we examined in Part 4. Every chemical bond in your body depends on electrons occupying specific shared orbitals between atoms. Those orbitals cannot survive in a field of 10 to the 15th Gauss. The electrons are pulled into field-aligned configurations that have nothing to do with the molecular architecture of organic chemistry. The bonds break, not because of heat, not because of explosive pressure, not because of gravitational stretching, because the electromagnetic environment simply no longer permits those bonds to exist in their normal form. The result is molecular dissolution. Every organic molecule in your body, every protein, every lipid, every strand of nucleic acid disassembled at the chemical bond level, rearranged into configurations dictated entirely by the geometry of the magnetic field rather than by the chemistry of life. You are not burned. You are not crushed. You are not stretched into a long, thin filament the way a black hole's tidal forces would arrange you. You are chemically unmade at the level of individual molecular bonds, simultaneously throughout your entire physical structure, without fire, without force, without gravity playing any role whatsoever. A black hole at least leaves evidence. The infalling material forms an accretion disk, emits radiation, produces observable signatures that instruments across the galaxy can detect. Forensically speaking, a black hole documents its work. A magnetar at close range leaves nothing that retains its original chemical identity. From the perspective of cosmic forensics, it is the perfect crime: no body, no evidence, no trace of the original molecular architecture remaining in any recognizable form. All of these mechanisms, the gamma radiation method, the direct field method, are either directly confirmed by observation or grounded in physical theory that has been validated to extraordinary precision. These are not speculative scenarios. They are documented physics applied to documented objects. But here is what is more unsettling than the mechanisms themselves: the question of when a magnetar chooses to employ them. Because unlike a black hole, which exists on timescales that make the age of the universe seem brief, a magnetar operates on a very different clock, and that clock is running faster than you might think, which makes every second of its active life more concentrated, more volatile, and more dangerous than anything a black hole could produce across 1 billion years of patient waiting. On March 5, 1979, a burst of gamma radiation arriving from the direction of the Large Magellanic Cloud struck a network of spacecraft and triggered detectors that had never recorded anything at that intensity before. Scientists eventually identified the source as SGR 0526-66, the first soft gamma repeater ever recognized as a distinct class of astrophysical object. For the first time, humanity had evidence that something out there was doing something the existing catalog of known phenomena could not fully account for. That was 1979, 46 years ago. In those 46 years, the confirmed Magnetar catalog has grown to approximately 30 objects. 30 confirmed, cataloged, studied magnetars in a galaxy containing between 200 and 400 billion stars. We have been looking seriously for less than half a century, with instruments that detect only the magnetars currently active and oriented in ways that send their emissions toward our detectors. The quiescent ones, those in the long silent intervals between bursts, accumulating stress behind a quiet surface, are invisible to us. The ones whose flares pointed in other directions are invisible to us. 30 is not a count of how many exist. 30 is a count of how many we happen to catch. The early warning systems we have built are remarkable pieces of engineering. The Fermi Gamma Ray Space Telescope, launched in 2008, monitors the entire sky continuously in the gamma ray band. The Neil Gehrels Swift Observatory detects gamma ray bursts and triggers automated follow-up observations within seconds. Integral, the International Gamma Ray Astrophysics Laboratory, contributes independent monitoring coverage across overlapping energy ranges. When any of these instruments detects a significant gamma ray event, automated alerts propagate to the global astronomical community within seconds, enabling rapid coordinated follow-up observations across wavelengths and observatories. This system is genuinely impressive. It represents decades of international collaboration and billions of dollars of investment in humanity's ability to watch the high-energy sky. It cannot warn you before the radiation arrives. This is not a limitation that better engineering will eventually overcome. It is a physical constraint built into the structure of causality itself. The gamma radiation emitted by a magnetar giant flare travels at the speed of light. Any electromagnetic signal we might use to communicate a warning also travels at the speed of light. Both depart the magnetar at the same moment. Both cross the intervening distance at the same rate. Both arrive simultaneously. A magnetar located 1,000 light-years from Earth fires a giant flare. 1,000 years later, the radiation and the detection signal arrive at Earth at the same instant. The warning is the event. There is no interval between them that could be used to respond, and when that radiation arrives, there is nothing to hide behind. High-energy gamma rays from a magnetar giant flare penetrate meters of reinforced concrete without meaningful attenuation. They pass through tens of centimeters of lead, the heaviest practical radiation shielding material available, as though it were tissue paper, at sufficient energies. The nuclear bunkers constructed during the Cold War, engineered to protect their occupants from the blast overpressure and initial radiation pulse of nearby nuclear detonations, are not designed for and would not survive as adequate protection against the radiation flux of a close giant flare. Earth's atmosphere absorbs and scatters gamma radiation, providing meaningful protection under normal circumstances. But if the ozone layer has already been destroyed by the leading edge of the flare, which occurs at longer ranges before the direct lethal radiation dose becomes the primary concern, then the atmospheric column's protective contribution is compromised, even as the direct radiation continues to arrive. There is no material currently available, no structure currently buildable, no geometry of shielding currently conceivable within the bounds of accessible engineering that provides complete protection against a giant flare at close range. This is not a gap waiting to be filled by future technology. It is a consequence of the energy scales involved relative to the physical properties of matter. Here is the honest accounting of where we actually stand. No magnetar currently confirmed in any catalog is positioned within a dangerous range of Earth and in an active flaring state. The scientific community monitors the high-energy sky continuously. The nearest confirmed magnetar in the well-studied catalogs sits at approximately 10,000 light-years, well beyond the threshold for serious biospheric damage. The current situation, based on current knowledge, is genuinely safe. But we discovered that magnetars exist in 1979. We have been cataloging them for 46 years. We have found 30. We do not know how many are quiet. We do not know how many fired in directions we did not detect. We are working with 46 years of observation in a galaxy that is 13 billion years old, trying to characterize objects that spend most of their active lives in silence between bursts. The good news: no magnetars targeting you right now. The news that follows that if one were, you would not have time to finish worrying about it before the concern became irrelevant. But perhaps the most clarifying thought to carry from everything we have examined is this. We have spent 12 sections walking through what a magnetar is and what it does, and across all of that, the density, the field strength, the crystal crust, the starquakes, the giant flares, the reach across 50,000 light-years. We have not yet addressed the single feature that, in some ways, makes a magnetar more psychologically unsettling than all the rest combined. Not how it kills, not how far its reach extends, but when it acts, and for how long. Because compared to a black hole, which persists across timescales that make geological epochs look brief, a magnetar lives on a completely different clock, and that clock makes every second of its existence more violent, more concentrated, and more dangerous than anything a black hole has ever produced across a billion years of patient, silent waiting. Think about Yellowstone. For most of its 2 million year existence, the supervolcano beneath Wyoming does almost nothing. A few geysers, a little steam. But scattered across that span are brief windows when it erupts violently enough to bury a continent in ash. The eruption is a tiny fraction of its life. It's also the only part anyone remembers. Or think of a 2-year-old mid-tantrum in a grocery store. Short, unscheduled, total chaos while it lasts, then calm again as if nothing happened. A black hole is nothing like either. Per the theory of Hawking radiation, never directly observed, but mathematically well supported, a stellar mass black hole will persist for trillions of years before evaporating. It doesn't need to hurry. It just waits, doing nothing unless something falls toward it. A magnetar plays by different rules. Its active phase, the window where it can produce starquakes and giant flares, lasts roughly 10,000 years. That's about the same span separating us from the start of the Neolithic Revolution, when humans first cultivated wheat, agriculture, writing, empires, world wars, the moon landing, the phone in your pocket. All of human civilization fits inside a single magnetar's active lifetime. To the universe, our entire history is one breath. Researchers, including Cuveliotu and colleagues, and later Kolpe and colleagues, arrived at this 10,000-year estimate by measuring how fast a magnetar's field decays. Every second, it loses energy radiating outward, cooking its own crust from within. There's no recharge. What it's born with is all it gets. Eventually, the field drops below the threshold that defines a magnetar, and it settles into an ordinary pulsar or a quiet neutron star, still extreme, but no longer monstrous. In that window, though, it doesn't sit idle. Studies of known soft gamma repeaters suggest a single magnetar may produce dozens to hundreds of giant flares across its active life, plus countless smaller bursts, each still more violent than anything Earth's geology has ever managed. 10,000 years, dozens to hundreds of civilization-ending scale events. No calendar? No countdown? If a magnetar had a motto, it would be, I don't need to live long. I need to live loud. And within that brief window, Nothing about its behavior follows a schedule and unpredictability not even a black hole can claim. Picture two drivers on the same highway. One signals early, brakes predictably, you can model their next move. The other is drunk, swerving with no pattern. The first is the safer driver even at speed. The second is the more dangerous one, precisely because no formula tells you what happens next. Insurers make the same distinction. Car accidents and even hurricanes follow patterns regular enough to price. A black swan event sits outside any historical pattern, survivable only by luck, not preparation. A black hole belongs entirely to the first category. Its mechanics are so reliable that astronomers predict orbital paths years in advance, approach it on a known trajectory, and the outcome is calculable before you arrive. A magnetar belongs to the second category. A giant flare happens when the crystalline crust finally fractures, but the exact moment can't be calculated, any more than seismologists can predict the precise second a fault line slips. We know stress is building. We don't know when it breaks, and on a magnetar, each break is roughly 10 billion times more destructive than Earth's worst earthquake. Between major flares, a magnetar can stay quiet for years or decades. SGR 1900 plus 14 sat in apparent calm before its major flare in 1998, documented by Hurley and colleagues. The silence gave no statistical warning. It wasn't safety, just the part of the process with no visible output. Three things put a magnetar ahead of a black hole. Reach a black hole needs your approach. A magnetar's flare fires in every direction at once. No approach required. Predictability. A black hole obeys calculable orbital mechanics. A magnetar obeys no comparable schedule. Speed harming you near a black hole requires your own motion. A magnetar's gamma radiation only requires that you exist within range when it arrives. At the one speed limit, the universe never breaks. Across its full 10,000-year life, a single magnetar releases roughly 10 to the power of 46 to 10 to the power of 47 ergs total, with a danger radius reaching several thousand light years, a meaningful fraction of the galaxy's stellar population. Rhea and colleagues, in 2013, documented a magnetar sitting just 0.1 light years from the galactic center, suggesting the galaxy's crowded inner regions may be among its least hospitable for life. And yet, Earth is still here. 4.5 billion years, never erased by a nearby flare. Part of that is luck. Part of it is simply geography. We sit in a quieter stretch of the galaxy, far from where magnetars cluster most densely. None of this is meant to frighten. It's meant to earn a little respect for the scale of what's out there, and for the quiet, improbable conditions that let us live long enough to learn about it. After atoms bent into needles, a crust harder than anything ever forged, and gamma radiation crossing the galaxy in 1/5 of a second, maybe it's time for a more honest name. Call it the universe's way of saying it's done with your problems. But the truly unsettling part isn't that magnetars exist. It's that we've confirmed only 30 of them in a galaxy of 2 to 400 billion stars. How many more are out there right now? Silently building pressure behind a dam none of us can see. We've now walked through 7 layers of something the universe didn't build to kill us, though it could, easily, without even trying. It built it. It seems simply because it could. As if to test the edges of what we're capable of understanding. 30 confirmed magnetars in a galaxy that may quietly hold thousands more silent right now, somewhere in the dark, storing energy behind a dam no telescope has spotted yet. Not aimed at us, or aimed at us, and we simply don't know it yet. And still, Earth is here, 4.5 billion years, untouched by a giant flare close enough to matter. Not pure chance, but not far from it either. A kind of statistical grace we rarely stop to notice. We stand at the edge of what we understand, and from that edge, the universe doesn't look like a threat. It looks like an invitation. Maybe the real question was never whether a magnetar could end us. Maybe the real question is how much more is still out there, unnamed, in the dark? And when we finally name it, when we understand it, that won't be a moment of fear. It will be once again proof that the human mind can reach into any dark corner of the universe and light it with curiosity.